These are notes on chemical and physical changes and or reactions. So just a little semantic note. If you're talking about, if you use the word changes, you can say a chemical change or a physical change. If you're using the term reaction, that solely refers to chemical changes. So you can have you have a chemical reaction. There's no such thing as a physical reaction in chemistry. Okay. So first, let's look at what we're going to use for these notes are atom, compound, molecule sets. Okay, and we're going to use some of these in class as well. So here are several different pieces that I took pictures of. So the red one is generally oxygen, and this is true of pretty much any molecule set that you get out there. Red is typically oxygen, and it is a piece with two little holes on it, 1, 2, because oxygen can bond twice. Then the little white one is generally hydrogen, and it has one little hole on it because hydrogen can bond once. And then the larger black one is carbon, and you can see 1, 2, there's a third one here, and there's actually a fourth one underneath. Carbon can bond 4 times, so it has 4 holes on it. And then we have some shorter non-bendy bonds, and then some longer bendy bonds, and we'll figure out when we use each one. So we're going to be using these sets. I use them through the notes, but we're also going to be using them in class. So we can then use them to make things. So for example, I can take a carbon piece, and let's see, here's my carbon piece, and then I can take 2 oxygens, 1, 2, and I can make carbon dioxide, CO2. And so remembering one more time, and we talked about this earlier, that this 2 refers back to the O. And now you start to see why there are maybe double bonds. So these holes, the number of times something can bond, that's not just like how much they could bond, it's how much they have to bond in each compound. So carbon always has to have 4 bonds. So if it's only bonding to 2 things, it's got to bond twice to those things. So we have a double bond here, and that's why we use the nice long bendy pieces. And we have a double bond there. And then oxygen can bond twice, so it's got to have 2 bonds. If it's only bonding to one thing, it's got to bond twice to that one thing. We could also make water. Water, we've got hydrogen that only bonds once, and then we've got oxygen that bonds twice, once to each hydrogen. And so that's why we get a single bond there. Obviously there's a little more to this that you'll get into in chemistry, but now you're kind of starting to put the pieces together. Oh, very literally. That's funny. Pieces together. Anyway, we see here water, and then the 2 again refers back to the hydrogen. So we have our 1 hydrogen and 2 hydrogen, and this would be a water molecule. And so we can use these to examine physical and chemical changes. So let's first look at physical changes. Physical changes are changes that do not change the way atoms are bonded to one another. So it's possible in the past you've learned other little tricks, like some people say physical changes are reversible but chemical changes aren't. Some people will say like physical changes are changes in appearance but chemical changes aren't. None of those are actually 100% true. Because, for example, if I cut my hair, that's a physical change. That's not reversible without me growing more hair. There are plenty of chemical changes that are reversible. In fact, when you take chemistry and you learn about equilibrium reactions, those are all reversible reactions. And then the change in appearance, anything could change something's appearance. If I bleach my hair, that's a chemical change that has changed the appearance of my hair. So really the only definition of a physical change is a change that does not change the way atoms are bonded to one another. So for example, if I have carbonated water, and this here's carbonated water, here are my little water molecules, okay, and then here's my carbon dioxide. And if it's for example, in the bottle, and the bottle is still sealed, it's pressurized carbon dioxide. It's actually pressurized to the point where it's liquid instead of gas. That's why you don't see the bubbles inside the bottle when it's still closed and sealed. However, when you open it, all of that pressure so the pressure leaves the bottle, so the pressure inside the bottle decreases. That allows the carbon dioxide to come out of solution. So here it's all mixed in, and in fact the carbon dioxide, because it's been pressurized, is liquidy, is liquid, not liquidy, sorry. And then once you decrease the pressure, you get uncarbonated water, or what we would call flat. So here's our water down here, and then the carbon dioxide bubbles out and goes out into the atmosphere as gas off on its own. So, you know, we could even like draw a little beaker around this. There's our beaker. And then, so we're left with just water, and the carbon dioxide floats out into the air and goes off on its own, unconnected to anything else. But the point here being, when that soda goes flat, we would say that that's a physical change, because it hasn't changed any way that the atoms are bonded to one another. So here, the hydrogens and oxygens are bonded. There's 2 hydrogens to 1 oxygen here, 2 hydrogens to 1 oxygen there, water molecules. Here, the carbons are bonded to the oxygens, carbon dioxide. Here, the atoms, carbons, hydrogens, and oxygens, have not changed how they're bonded. They've just changed their location. Instead of the carbon dioxides being dissolved in the water, they're floating out into the atmosphere. And we're going to look at this change in a little more detail in the coming days. So then let's look at chemical changes. Chemical changes, again, you can have a bunch of ideas that may help you narrow down your choices as to whether something's physical or chemical, but at the end of the day, the only thing that is 100% true is that chemical changes are changes that do change the way the atoms are bonded to one another. So here I've got hydrogen gas, H2, and then this is oxygen gas, O2, so this is the oxygen gas that's in our atmosphere. And now again, you can sort of start to see why it's a double bond, because each oxygen has to bond twice, and there's only one other thing it's bonding to, so it bonds twice to itself. So let's look at what happens when hydrogen gas and oxygen gas go through a chemical reaction. And as you may remember from the space shuttle taking off video, that big cloud that was water vapor, and that's because in the big orange tank there's hydrogen gas and oxygen gas, and when those two things combine, you get water. So here we've got, same as before, we've got our hydrogen gas, and then here we've got our oxygen gas, and now I'm starting to give you a little of the notation of chemical reactions, and this gives you, and we'll talk about this in a minute, water. So you can see the atoms have changed the way they're bonded. Instead of the hydrogens being bonded to each other and the oxygens being bonded to each other, the hydrogens are bonded to an oxygen. Changed the way atoms are bonded. So let's break this down a second. So here's our hydrogen gas, so we'd say H2 plus, we actually use the plus sign and we just say plus, O2, and then this is called a yield sign. So this arrow here is called yields, and yields means makes or gives you or produces, and then we have our H2O. So we would write this chemical equation as H2 plus O2 yields H2O. Now, some of you are kind of almost jumping up and down hoping that you can ask a question at this point, because you're saying, where did the other oxygen go? So if we look at this equation again, you'll notice here we've got 2 hydrogens, and here we've got 2 hydrogens. Here we've got 2 oxygens. Here we only have 1 oxygen. Well, this is getting into a chemistry principle called balanced equations. And in talking to your physical science teachers, they said you didn't really get as far as balanced equations last year. We know, based on the law of conservation of mass, that whatever mass we have at the start should be the mass that we have at the end. we should be able to account for all the mass. So if we go back to our physical change, whatever mass we lost from the soda should be the mass that has gone off into the air. That's that carbon dioxide. That makes sense. If I shave my pencil or sharpen my pencil, physical change, then the mass of the pencil at the start should equal the mass of the pencil at the end plus the shavings that I have. Physical changes make sense that the mass would stay the same, but that mass should stay the same in chemical reactions too, which means that this equation isn't balanced. And I like to think of this is our general equation here. So this is like saying, in order to make cookies, you take some eggs, you take some flour, you take some sugar, you take some chocolate chips, you take some oil, and that's how you make cookies. And that's great, but it doesn't tell you anything about the amounts, right? How many eggs do I need? How much sugar do I need? And so, in order to know that, you need amounts. So, in order to balance this, you would need to know the amounts that you need in, and we're going to now give this a title. We're going to call anything that's reacting, we're going to call reactants. So that's REA, reactants. So your reactants are your hydrogen and oxygen gas. And then on the other side of the yield sign, what you get are the products. And remember, yields means produces, so that makes sense. And some reactions, as I talked about earlier, are reversible. And there's still reactants and products, and we're not going to worry about that at this level, though. But I did want to kind of put that out there because I had mentioned it earlier. So this doesn't tell us how many reactants we need and how many products we get, right? Right? If this is how you make cookies, okay, how many cookies? A dozen, 4 dozen, 3? What am I going to get? So we have to do what's called balance the equation. And I'm not going to get into detail right now about how you balance the equation. If you want to know, feel free to ask, like during work time in class or after school, or you can look it up. You will learn it in general chem. But I know some of you really want to know what happened to that other oxygen, so that's why I wanted to bring this up. So this is the actual equation. In fact, what you get in the reactants are you have 2 molecules of hydrogen gas plus 1 molecule of oxygen producing 2 molecules of water. And so the way we actually write this equation would be 2 H2s, okay? Plus O2. Again, similar to like in H2O, we don't need a little 1 subscript here. If there's only 1 oxygen, we don't need to put a little 1 in there. Yields 2 H2Os. And so this is what we call the balanced equation. And I also think that's important for you to know right now because we're going to be seeing balanced equations all year long. So now you'll know what they're called coefficients, these big numbers, mean. Please feel free to put questions on YouTube or ask them in class. Have a good night.